Welcome all of you to fluid mechanics course. Today I am going to deliver lectures on conservations of momentum. As you know it, in the last class we discussed about conservations of mass. Also we have solved few problems based on the conservations of mass. The basically we have been following the Reynolds transport theorems, the basic concepts to apply the set of the system physical equations to the control volume level, and then at the control volume level we have approximations of extensive and intensive properties, and that is what we have as of now we have already derived mass conservation equations. Today I am going to derive conservations of linear momentum. Again I can tell you that book wise the Singhal-Shimvala, the fluid mechanics fundamental applications, this is the book has given very clearly the illustrations of this concept of Reynolds transport theorems, the conservations of mass, the conservation of linear momentum, angular momentum, and the energy concepts. So, which is more descriptive type, and that is what is gives enough to a student to understand this concept. Now, let us come back to the last class what we studied. As I told it, we discussed about the Reynolds transport theorem for conservations of mass, and when we apply this conservations of mass for the Reynolds transport theorems, we have two basic assumptions, either with respect to time is steady or unsteady. So, the steady we do the approximations of many fluid flow problems is steady problems. Then we with respect to density change or the variations of the density, we divide it flow is compressible or incompressible. So, we can have a two type of approximations, steady compressible, steady incompressible. So, when you have the steady assumptions, as you can remember it that we the component of Reynolds transport theorems of time differentiate components becomes 0. So, or the volume integral component part of the Reynolds transport theorems becomes 0. So, it becomes a very easy problems with you have only this surface integral components and the is equal to 0. So, that the very simplified case that, and when you density is a constant, that means what it happens is densities comes out from the equations, which makes us only this scalar product between velocity and the normal vectors. That what is a scalar quantity, we do the surface integrals with respect to area. So, that is the problems becomes too simple as compared to if you have a flow of compressible flow. So, when you have a steady incompressible flow, most of the case what we consider for flow devices or engineering applications, we can consider steady incompressible flow, then the problems becomes very simplified when you apply for Reynolds transport theorems. As you remember, we have a lot of there are examples starting with tanks with multiple inlets, the estimation of seepage losses in the laboratory flumes. Also, we discuss about Ganga Brahmaputra confluence at the Padma. So, how we can have this mass conservation equation for that. Then the estimations of percolations in a soil matrix. Today, I will repeat this equation, the problem, how to these things. Let me come back it to today's lectures, what I will cover it. First, again I have to give a few examples on conservations of mass. Then we will go for to write the linear momentum equations for fixed control volumes or the moving control volumes. Then what are the simplifications need to be done it to before applying linear momentum equations. That what we will discuss it in terms of non-considerations of atmospheric pressures, then what is called the momentum flux correction factor, how we use it That what I will discuss it. Then I will show the jet experiment, impact of the jet experiment, then I will summarize it. So, let us come before going to this thing, if you could have heard of these projects, one of the hydro project one is one of the largest project in our countries, which is Bhakra Nangal projects. Okay. If you look at this Bhakra Nangal projects have the reservoirs which is about 88 kilometer long and 8 kilometer wide, and total capacity, the water storage capacity is about 9.34 kilometer cube. So, huge amount of waters as a storage, if you can see in this type Google Earth imageries. The dam is located here, which is a concrete dam and having the height of 207 meters approximately, and the length is 500 meters, and width varies from at the top 9 meters, as goes down the base becomes wider and wider, which will be the 191 meters. So, what I am to say is that if you look at these projects which was initiated, commissioned early 1950s and 60s, generating the installing power of hydropower projects about 1300 to megawatt powers. So, what you look at that the basic fluid mechanics knowledge, that is what is used to design so complex, so these hydropower projects. So, the basic fluid mechanics what we have, that is what is used the way back in 1950s to design these Bhakra Nangal projects, which is one of the successful projects in our country. So, if you look at this way, we will take it a lot of hydropower projects, and I will tell it how to estimate the power potentials, how to estimate the what could be the turbine speed. All we can do it. It is not a difficult task as if you have a knowledge of the fluid mechanics. So, only the knowledge of the fluid mechanics and the civil engineering excellence helping us to generate the powers at the order of 1300 megawatt powers without any polluting the environments. So, the hydropower projects, they have the strength, also there some disadvantages are there, but there are the projects that are implemented, and those project components we can understand if you understand the fluid mechanics well. That is my point to note to you for this. Let us come back to the example. The last time we discussed these problems, again I am to repeat it to just for more detailed understanding of these problems. Let us consider there is a soil matrix, that means there are the soils are there which is having a porous space, and in that soil the compacted the soil component we have the flow, the water is coming, it is a Q1, Q2 and Q3 is going out, and at the bottoms this is a percolation type or seepaging, the water is coming out from the soil matrix as it has the soil moistures are there, the soil in the porous space of the soils there are waters are there, that is what is a coming as a seepage water to here. Here this Q is a functions of storage within the soil matrix, and the K is a constant proportional, or we can call hydraulic conductivity. So, Q1 is given for this study, Q2 is given, Q3 is given. So, I have taken this is my control volume, this is my, if you look at the yellow colors is a control volume. If that is the control volumes, before applying this conservation mass, I should classify the problem. The problems what natures is a one dimensional flow. The flow what we can consider across this control surface are the one dimensional natures, that is the unsteady, the flow will be the laminar, and the control volume is a fixed and incompressible flow. So, these are the flow classifications, or you can say these are the assumptions. This is what help us to simplify these problems, and whatever the data is given Q1, Q2 and Q3 in terms of liter per seconds, and Q as a function of Kx plus 0.1 is a linear function between the storage and Q, and that the constant of the linear functions with the K is there, which is a constant quantity. Now, if I apply, so now I have simplified the problems, I have to apply under this control volume the basic mass conservation equations. It is a unsteady equations, okay, with a 2 inlets and 1 outlet. That is what you can know. With the 2 inlets, the Q1 and Q2 are inlet, Q3 is the outlets. Then there are the outlets is a seepage part which is coming out, which will be the in terms of S. Yes, if you look at when I consider this the control volumes with having the Q1, Q2 the inflow and the Q3 is outflow, and the small q is also outflow, which is a functions of with respect to S the storage, the control volumes K 0.1, which will be the unit will be the liter per second. So, if that, then I just apply the unsteady flow equations, conservations of mass. This is what the volume integral part, if you remember it, and these are the, since it is a one dimensional part, we have the negative for the inflows and the positive for the outflows. So, we can find out this Q3s and all are the mass influx in, mass flow out, and that was the integration, and this part is the storage is S. So, dx by dt q1 plus q2 and this just rearrangement of this and substituting this value will get it ds dt is these functions, okay, and we can integrate it, finally get a relationship between T and S as the K is the constants is equal to C. So, if you have the boundary conditions, we can determine the C value, then we can know what is the functions of the S, how the X varies with respect to the time. That is our problems. So, that way if you look at very complex problems like this, when you have a soil matrix and porous structures and you have the flow of Q1, Q2, inflow is there and outflow is there, the seepage is a function of the how much of water storage within the soil matrix. We can apply a simple mass conservation equations for these control volumes, then we can integrate it to get it what is a function of x with respect to time, and that what will give us from this. So, this is what the problems again I solve for you. So, now let us come to the example 5, which is the GATE 2006 civil engineering part. In that problems, the velocity field is given it. If you see this, the scalar component of the velocity field, in which there is a component of lambda is unknown to us. Okay. Density is also varies with respect to the time, rho naught into exponential minus 2t, that means minus 2t, that what is the densities varies, that means is a unsteady problems, and the velocity fields are given. In order to have a mass is conserved, so that the point is that mass is conserved, then what could be the value of lambda, that is what it will determine. So, that means what we will do it, we will apply the mass conservation equations, and once that mass conservation equation is satisfied, from that mass conservation equation we will compute it what will be the lambda value. That is the problems here. So, let me classify the problems. Problems will be the unsteady, maybe laminar or this, but fixed control volume, and since the density is varying with the time, so you can say it is a compressibles could be. Okay. That means is some sort of the control volume like this, you have a ds like this. So, applying this control volume approach, equations for unsteady flow, you will have a this component and this component, which already we derived earlier. Let me put it this form. Okay. The time derivative part of the control volumes, that is what we will have a this part. See, if you look at these surface integrals, if I follow this Green's formula, okay, these surface integrals can be converted to a volume integrals in terms of delta operators. Okay, if you remember the Green's formulas, we can convert this surface integral to the into the control volume levels with having a delta dot products. That what the concept we could have known from the mathematics point of view. Now, if I have a that part and if you do the integral part I can go out, then finally the equations becomes this, because when you do a integration over that can come on, we can take it out, then you will have the rho, the partial derivative of rho with respect to time, then you will have a dot product of delta operated and the rho into v. So, we give you this rho into v, this product will be rho u as a scalar component y. If this u v w is a scalar component, you can get this component is this ones. Okay. Now, I am just substituting the density into rho, density into v, density w in these equations. Finally, I get this relationship, and this relationship finally give me the alpha value, lambda value, which is equal to -8. So, this is the problems what is solved it. So, basically this equation is conservation's mass what we have applied it, but to since the velocity vectors are there which is having 3-dimensional velocity vectors and the density is a function of the time. So, we have applied it as bringing it to this level, then we have solved it for the lambda value. Now, if take it another examples which is given in GATE 2012 civil engineering specializations. There it is a very simple problems like what is given in these diagrams. Okay, there are the pipes is there and there is a joint which is called a T joint like this. P is a inflow is coming, Q is going out from this, R is going from this out. So, by pipe having branching of P, Q, R, the diameters are given it, the velocity Bp and Pq is given it, B are to be estimated, which is very simplified problems. You can see that this problem is one dimensional, the steady, the velocity is given in, the circular pipes are the pole, the flow could be laminar or the turbulent, okay. We do not know it, fixed control volume and incompressible. So, these are very simple problems as looking into these, that we will just apply the control volume and try to find out what will be the mass influx is coming into this and going out. So, basically if you try to remember in mass influx, mass per unit time coming in should be equal to mass influx from going out for steady problems. So, being a steady problems, what you will have, the mass influx what is coming it, rate of the mass influx is what is coming in should have equal to rate of mass influx going out from this control volume. That is the things. So, in this case, because there are two outlets, so some of these two mass outlets going out from this, that is what we equal to mass influx what is coming it, mass flux rate what is coming it, the mass per unit time what is coming it. So, that way you can see that if you have a rho q in, a very simple way it is rho q in will be the rho q1 out plus q2 out. That is the basic concept. Since same density, that means you have a q in is equal to q1 out or q2 out, two outlet. So, sum of the two volumetric discharge is equal to the inflow volumetric discharge what is going. That is very simple problems, only you have to compute since the velocity is given it. So, Q will be the A into V, that is the basic concept. The area into the velocity is a Q, average velocity is given to us. So, we can compute it the discharge and we just apply the Q in is equal to Q1 out plus Q2 out. So, numerically that is what is coming it. For the steady flow this becomes 0. So, you have a in and out. So, as you know this in will be the negative and the out will be the both will be the positives, and substituting these Q values for all the cases with a VR unknown. So, finally substituted to these equations we will get it the VR equal to 4 meter per second. So, there is very simple form of solving these the pipe problems where you have the one inlet and two outlets. So, as the incompressible flow, the density is constant. So, you just do a volumetric flux coming in is equal to the sum of the volumetric flux going out from the control volume. That is what we come with. If you do not remember that, very simple way you remember it, that the mass in flux or rate of change of mass with respect to time coming into the control volume should be equal to the rate of the mass going out from the control volume, that should be equate each other, that should be equal. Inflow and the mass influx and the outflux rate should be equal. That the concept what we consider it for steady flow conditions. Now, let us coming to the to derive the linear momentum equations. Okay. So, we are going for solving these flow problems for a linear momentum equations. So, that means we will consider the control volumes. That is the we have considered the control volume like this. So, each control volumes have the control surface. It would be a very simple tetrahedral type of structures, or you can have a very complex. It does not matter it what could be the shapes. Okay. Can have simple shapes or it can have a very complex shape. So, if you look at that over that surface, what will happen it? You will have a normal vectors. Let be the dA is the surface area. Over that, this is the normal vector to the area, to the surface area. So, you will have the surface which will have a two type of force is going to act on this. One is body force, that because of the mass of the control volumes, how much of body force is giving say gravity point of view, or other forces we do not consider here is electrical or magnetic field point of view. So, the basically because of the control volume mass, how much of weight you are getting it, how much of body force you are getting it, that is what will be the body force. And the surface, along the surface what are the force is acting is, that is a surface force. So, you have a two force components you get it for a control volumes. One is the body force, another is surface force. The body force acting entire body, that is what is mostly oftenly we use is the gravity. Other electric and magnetic fields are not considered for this case, but some cases we can consider it. Other is the surface force act on the control surface. So, what are the force can acting on the control surface will be the pressure force, the viscous force and any reaction forces. Okay. Like a control surface is cutting through a surface, a rigid part. So, there could be a reaction forces will be there. So, that way if you look at that, if we take a control volumes, there result to be a two type of forces. One is a body force which is act throughout the entire body, that depend upon the mass what present within the control volume. Another is that over the surface of control volume, there will be the force components. Those forces are due to the pressures, viscous forces, because of viscosities of the fluid flow systems, there will be the viscous force component and also reaction forces or the other force components which comes it. Now, let it find out what will be the gravity force, which is very easy things, that if I take a small element dV, I will have the weight of these small control volumes will be the rho g and dV. So, please look at the unit of each component, if you can understand it, that the mass will be the rho into dV will be the mass, dV, V is here look for the volume, mass into the g is the gravity force component. Here the gravity force components we can consider as a g is a vector quantities of any directions, but you can align with if the y is upward of directions, then you can the k notations we can use it to define the g vector components. Okay. So, the basically if I consider the total control volumes, then the sum of the force or integral, the
volume integrals of this component rho g dV, that will be the gravity part, or indirectly this is what mass of the control volume into the g. G is the acceleration due to the gravity vector components. And many of the times we align the z axis and g is a downwards, then we use the negative, not the scalar quantity, not the as a vectors representation. But if you have consider the different orientations of the control volumes, then you can consider g has a vector quantity, it has a scalar component of gx, gy, gz in 3 respective scalar direction of x, y and z. Now, let us come back to what type of force acting it is. That surface forces are as we discussed earlier, that will be the any surface forces will have the normal component as well as the tangential component. There will be a normal component, there will be a tangential component. And let me take it these figures, which is very interesting figures, is showing to you that this is the control surface having the area of the dA. It is the normal vector, n is this part is a normal vectors. So, if your force acting on this having a angle, so then you have a this force can have the two components, one for the component for the normal, another for the tangential component. Okay. So, the control surface can consider any orientations. Okay. Over that you have a normal vectors, which is the normal to the control surface there. So, if your force is acting any direct any at that points having a different angles, so then what you will happen it, you will have a normal component, also the tangential component. But if you want to result as a x and y component, okay, that is the Cartesian coordinates. So, that is what is a different here. One is a Cartesian coordinate level resolving the force vector component to a scalar component in x and y direction. Another one is we are resolving this force vector, the force component into the normal or the tangential component. That what here is illustrated here, is that how you can have a two different components. Now, if you come back to the surface forces, okay, like for example, for a tetrahedral structures like this, where you have a dx, dy and the dz is component is there, and your axis is like this, x directions, y directions and the z directions. So, you can define the surface forces are as a trace tensor. Trace means what? Force per unit area. So, you can define as a trace tensor. So, this trace will have a 9 components. You could have this knowledge in solid mechanics. I am just repeating it. There is not much difference between solid mechanics to the fluid mechanics when you consider as a trace level. So, we have a trace tensors, okay, in order to describe all the surface force components. That is what will have a 9 component, which will have a, as you know, the subscripts describes that the trace in the z directions acting on the face, which normal is the I direction. This is a similar notations what we use in the solid mechanics. So, you have the trace tensor coordinate systems defining of the 9 trace components. If you look at that, if you take it these diagonal components, which is the normal component to this surface like sigma SS, sigma ZZ, these are all normal components. That means, these are compositions of the pressure force and the viscous force component. But if off diagonal components, what we have this sigma xy, sigma xz and all, which is acting on tangentially. So, basically these are the viscous terms. These are the viscous terms what it works it. So, over the surface we can define it, which either the shear stress components or the viscous stress component what we get it. So, these 9 component of stress tension Cartesian coordinates which define this surface. So, we can solve the problems considering the surface force defined as stress tensors and defining as a normal stress and the shear stress component. The normal stress is a composition of the pressures and the viscous stresses, whereas shear stresses most it's only the viscous stresses what we get it. Now, if I have the stress components is there and I have the normal vectors, if I resolve the force components, I will have the scalar product between the stress tensor and the n vectors. That is what we do it. And for the total surface area, we do a surface integrals to compute it. Okay. Please do not be have a more worried that how we are defining having a scalar product of a trace tensors and the normal vectors, which will be coming to be again a second order vector components. You try to get the mathematical point of view with that, and or different literatures nowadays available, you can understand the physics behind that, how mathematically we represent the stress tensors and the dot product or the scalar product of the stress and the normal vectors or any vector quantity. So, if it is that, so you can integrate it to get it all the stress components. So, total force acting on the control volume will have the body force component, surface force component. The body force component will have a volume integrals of rho g dv. G is the vector quantities, as we consider the g acceleration due to gravity can have a vector quantity with 3 scalar components of gx, gy, gz. That means what I am defining, g can have a gx, I, gy, j, gz, k. So, you can define like this, okay, to make it, but many of the times we make it alignment such a way that only these kth directions of negative directions, okay, and k is in upward directions, we define the g, that becomes a scalar quantity along acting the downwards. That is what it happens it, but if you are solving the problems where you do not know the directions of g vectors, okay, which could be gx, gy, gz, then you can need to do this the volume integrals to solve the problems, and this is the surface integrals over this control surface to get it what is the force acting on the surface. Then we will go for simplification these ones. If you look at these things, it looks very complicated that we cannot apply it for a simple example problems what we encounter as civil engineers or mechanical engineers, that what is the total force acting on the surface will be the body force and the surface force, and this is two integrals we are talking, one is volume integrals, another is surface integrals. Now, if you look at, if I divide the force components, that means the total force will be one component from this body force is a gravity force component. The surface force component we can result it into the force due to the pressures, force due to the viscous, force due to the other reactions, that means the reaction component of force. See, if I resolve this force component and if we can have a simplifications like the cases where the viscous force is not dominated, then we can make it to 0, or other forces not dominated, we can make it to 0. So, that way we since we have resolved it or we separated the force component due to the pressures, due to the viscous and others separately, for different type of problems we can simplify these equations and focus on the force components only due to the pressures or due to the viscous, due to other component. Now, let us consider very important component before applying this linear momentum equations, that when you apply a linear momentum equations to a control volumes, like I have the control surface like this. If you look at this control surface, in these 3 phases we have the pressure is atmospheric pressures.
Here I have the absolute pressures, that means atmospheric pressure plus the gauge pressure. If I look at any control volume I consider, the control surface always will have a the pressure is equal to the atmospheric pressures. That means, if you can understand it, that if I take a control volumes, so everywhere I will have a atmospheric pressures, then the absolute pressure from some locations. So, if I consider the atmospheric pressures is acting throughout this control surface and do a surface integrals, if is pressure is having the directions each others, and if I do a surface integrals over this, it will be cancelled out, becomes 0. So, considering that, what we generally do it, we nullify the atmospheric pressure component, because as you know it, when we integrated the surface integrals of the atmospheric pressure for any control volumes, that becomes 0. So, we consider only the gauge pressures when you define the pressure diagrams for a control volumes. Like for example, in this case, if you look at this atmospheric pressure components are given it, and this direction this pressure is equal to P1, which is the absolute pressures. So, finally, what we do it, that we do not consider this pressure distribution, because as I said it earlier. So, this part will be the gauge pressures, the difference between the absolute pressures and the atmospheric pressures, that what will be the gauge pressure, what we will get it. Then we have the two force components is working, one is the body force component, another is the other reaction component. So, finally, we use this control volume, a simplified control volume, nullifying the atmospheric pressure distributions over the control surface. We consider this control volume and the pressure diagrams to solve the problems. That is what is that. The atmospheric pressures acts in all the direction, its effects is cancelled out in every direction, which performing the force balancing, or that is what I am saying it, when you do a surface integrals of these constant pressure distributions in a closed control volumes, that is supposed to be 0. That is what it happens here, all these direction and it is cancelled out each other. So, the pressure forces can be ignored at the outlets where the fluid is discharged at the subsonic velocity to the atmosphere. So, what is there? Another assumption which is quite valid is that if you have a subsonic flow, it is very almost all times in a civil engineering problems we get in the subsonic flow, okay, not the sonic or supersonic flow. In that case, the pressure force is generally we neglect it in that stage, as the discharge pressure in case is very near to the atmospheric pressures. So, if you look it and measure the pressure at that locations when you have a outlet sections, then that becomes a atmospheric pressure. So, we neglect that atmospheric pressure component if you have the free outlet discharge what you have. So, that the points what I am to tell it, that we work with a gauge pressures, okay, when you have defined the simplifications of control volume concept. Now, another point is that how to choose a control volume, because that is what the art, like you do free body diagrams in solving the solid mechanics problems. Similar way, the drawing the appropriate control volumes is art, that what you have to learn it by solving many problems using the control volume concept. Like for examples, what I need to do it if I do take these problems, okay. So, that means there is water is coming it and there is a bolt holding that the water outlet points, and there are the spigot and we have a water coming out. I can have a control volumes like as given is a CV control volumes, okay. I can have a CV control volume, which is just surface of the wall surface touching of only this the water part, if I consider the control volume. We do not know what is the stress acting on the over the surface, that is unknown to us. Also, we do not know what the pressure distributions at this point. So, when you draw this type of control volume, where over this control surface we do not know it, we cannot solve the problems.
Instead of that, if I take a control volume like this, is a control volume B. Okay? If I look at this control volume, very clearly I know it inflow, I know the weight component, one is water weight component and the another is weight component of this the tap or this spigot part. Then I also know this direction and Q out from this. So, if I consider these control volumes and over this P will be the P atmosphere. So, these problems will become simple. If I just want to know it how much of force is acting because of these flow orientations. So, I can compute the force components to find out how much of force is acting on this bolt. So, that is the point, is that it is a engineering skill or the art to be developed by the students, that how to use the control volume concept, how to define the control volume for a flow system, so that you can easily solve it. And another things what we do it, that when you define the control volume, the control surface should have a and the velocity should have aligned to that. That means what I am telling it, that if my control surface like this, if I have a normal vector to that, this is the normal vectors. So, B should have either 180 degree or in the same directions, making the n vector and the vector. So, if you do that, your scalar products becomes easy to do it. The cos theta becomes, if theta becomes 0, cos theta equal to 1, theta is 180 degree, cos theta will be minus 1. So, that way it is a simplified this vector product, where do you use these things, that the velocity and the normal vector, they should have either 0 degree or 180 degree. That is what my point is. We can consider the control surface which will be the with respect to velocity. We can take it any arbitrary shape, but when you take arbitrary shapes, if your B and N is not having 0 or 180 degree, the finally you will end up to do a scalar product, do a surface integrals to solve the problems, which more time consuming and laborious, but the results will be the same. So, that what you have to look at, that how to define the control volume and the control surface such a way that your problems, what the target of your problems, you have to solve it. That is the art. That is what the art I will discuss is today lectures. We will not talk about different type of control volume to use it. Next class onwards, I will show you that how we should use the appropriate control volume to solve the problems. Now, come back to that. Applying the Reynolds transport theorems, we have to write the linear momentum equations. If it is that. So, at this systems levels is a force equal to mass into accelerations. That means, at the systems level, force will be the mass into acceleration, as you know from basic solid mechanics. Okay. So, when I derive it at the systems levels, the momentum flux, that is what is the B, is my momentum flux. That means, that should equal to give me net force acting on that. That is what is the system. And at the control volumes levels, as B equal to mass into momentum flux, so small b, the intensive properties becomes velocity vectors. If I apply it with this, I will get these equations. So, this is the general equations for a control volumes. We can have a VR for moving control volumes, you can use the relative velocity components, and the V is the velocity vectors, and VR is the relative velocity vectors. So, the basic, this is the equations which is the linear momentum equations in Reynolds transport theorem point of view. These equations will be simplified to solve the problems, because as of now these problems we cannot solve it because it has a surface integrals, it is having also the volume integrals. So, let have a consider I have a fixed control volume, that means control volume is fixed. So, your VR becomes V in case of this. So, you have a volume integrals and the surface integral like this. this is what my control volume. Okay. This is my control volume. The flow is coming from this, flow is also coming from this. Okay, both the side flow is coming it, and there are the pressures is acting on P1, P2 and A1, A2, and there is a weight and there is a reaction force is acting on that. So, this is A1 and A2 and this is a pressure diagrams. If it is that, this force can have, as I said it earlier, we will have the body force component which is the weight, the pressure forces and the reaction forces at this point what we are getting the reaction forces. Also another reaction force is attached to this here. There is two contact points at this point this. So, we can use a gauge pressure as is that you need to do the integrations over this, you can use a gauge pressure at these 2 points to find out the pressure force component due to the flow. Now, let us consider a special cases like many of the times we have any industry, if you look at their network of the pipes and connected to the tanks and all. Similar way there will be a series of inflow, series of outflow. If you have that type of concept like this is a fixed control volumes, you have a series of inflow like 1 and 2 are the inflow and 3, 4, 5 are the outflow. So, through this control surface if you look at, we are talking about not only the mass flux coming into this control volume, but we are talking about momentum flux. The momentum flux will be the mass flux, mass per unit time into the velocity, that is what will be the momentum flux. So, through this control volume we know this momentum flux, through this control volume what is the momentum flux is coming into, through this control volume what is the momentum flux going out from this and going out from this case and this case. Okay. So, the basically if you look at that we can compute it the momentum flux coming into this control volume also going out. So, if you have a multiple inlets and the outlet, then you can find out how much of net momentum flux is there in this control volume. Just like we did it for the mass fluxes in mass conservation equations, here we are talking about net momentum flux passing through this control volume, which will be equal to the force, the net force acting on this control volume. The same concept what we know it force equal to mass into accelerations, the same concept we are considering here as a change of the momentum flux within this control volume, that what is will equal to the net force acting on this control volume. So, now let me look at that if I am considering is velocity distributions are there, velocity variations are there, then you know it this mass flow rate. Okay. Across this inlet and outlet we can have a surface integrals to find out the mass flux. So, it will be the average V average rho into AC. Similar way we can find out momentum flow rate, momentum flux. If you assuming it is a uniform inlet, that means your velocity is not changing it, V average is a constant, okay, or the velocity variation is not there, that is what you call the uniform velocity. Okay, that condition does not relate, but some of the cases we can simplify that. Okay. So, in that case if in a surface velocity does not vary, okay, so we can define as a mass flux rho Vg into AC, that what will be the mass flux, V average with the velocity, that what will give a momentum flux. So, here what we have considered as a uniform distributions of velocity, that is what not will go to in a real fluid flow conditions, that what will have a correction factor for that. So, if you look at that way, now we can write the momentum equations in different forms considering the velocity distributions. That is the reasons we introduce a correction factors. That means, as we know it, the velocity distribution is not uniform for real fluid flow problems. If I use the computing this momentum flux using the velocity of average velocity, then what could be the correction factor for that? That is what called the momentum flux correction factor. Let me repeat that thing. You know it for the real life fluid flow systems, like for examples, I have 3 examples here. Okay. The one of the example is that there is well rounded entrance to the pipe, that flow is coming from this very well rounded. So, you will see that velocity distribution will be there at the wall, you will be the 0, then velocity distribution will come and 0. Similar way, you have a largest pipe section, wind tunnel section, then it is coming a test sections like this. This is the test section. Okay, wind is coming that. So, you know it over this control surface, the velocity will have a 0 here, then distributions, then coming back to that. Or you have a free water jet is coming into a air. So, you will have a this. Most of the times what we have observed it, when if you have a flow is a turbulent, your no doubt you will have a 0 velocity at the wall locations, as this the pipes or the text section is at stationary at the rest conditions. The velocity distribution more or less uniform except at the wall locations. So, we can use the average velocity concept for that. The V can be approximate as average velocity for the all these cases. If not, let me have the pipe flow, okay, the laminar pipe flow. So, as you know it, you will have a velocity distribution not will be the 0 at the pipe contact locations, the maximum velocity will be at the centroid. So, there will be the parabolic distributions of velocity. In that case, as the velocity is not a uniform, so we need to have a correction factors for computing the momentum flux. If we are computing momentum flux using average velocity concept, that is what the correction factor. So, that what you try to understand it. So, if you are computing the momentum flux based on the average, then you should have a correction factor for that. So, okay. So, that what let have a this the momentum flux correction factor, which is will be the dimensional correction factor of beta, where the velocity acceleration most of inlets are not uniform. We can convert the control surface integral to algebraic form, that is what it is here. Okay. Because B average computations are easy, and you know this mass flows in and out for each control volume inlet and the outlets. So, you can compute the momentum flux, and since you are using the average velocity to compute the momentum flux, you also consider the velocity distribution in terms of correction factor, that is what the beta value in terms of correction factor. So, finally, your the surface integral part and the volume integral part will come like this. If it is a steady problems, this becomes 0. So, again you have a very simplified case, the sum of the force acting on that will be equal to the net the momentum flux passing through this control surface, that is what will become it. Okay. So, let have a this for a uniform flow. So, beta will be the equal to the 1, and these things, if I do the integrations of the velocities and the scalar products of B and N over a surface AC, and that what I am representing an average. So, beta will come it to be this part, or with a simplifications beta will come it this way, that if I know the velocity distribution, I know the average velocity, if I do these integrations and I know this surface area, then I can compute what will be the beta value for a velocity distributions coming into a cross sections. Like I have a pipe of laminar flow, pipe of turbulent flow, or it is a open channel flow is connecting. For each case we know approximate velocity distribution. So, that means for each case we know what is the beta value for that cases. So, if I know the beta values, then we need not to do the integrations again. We use that beta value to convert from average velocity data to the momentum flux. So, that the advantage to use the momentum flux correction factor. Now, let us before concluding today's lectures, let you see this the figures what is there. Very simple experiment is impact of the jet experiment. If you look at this jet, the water jet part is here and it's balanced by the weight here. So, we can know this what is the velocity of impact is happening it, and that what is how much of weight is we are counterbalancing it. So, if you know it, you can theoretically is you know it, this is the what the control volume, you have a water jet is coming it, and that water jet is going in these two directions. If you look at this photograph and these simplified conceptual diagrams, you can find out that. So, theoretically this will be rho a v square is a momentum flux, okay. Rho a and v square will be the momentum flux what is impacting on that, because in these directions the output momentum flux is 0. So, what is the influx, that is what converted to the force component, and you have experimental, then you find out what could be the, definitely there is a deviations from the experiment and theoretical, because any systems like these JAPT apparatus, it has some degree of losses is there. So, we cannot have exactly whatever the theoretical value, we will have a deviations from that. That is what we compute the error, the theoretical experimental, the deviations between the theoretical and experimental divided by theoretical into that what is gives us the error. So, this type of simple apparatus will be there any of engineering college. So, you can see that how the impact of jet, the force is acting because of jet impacting on that plate, that is what the conditions. This is a very simplified case, here is the impact is a normal to the plates, okay. You can have a many numerical examples where the plate can be inclined, the flow jet can have a inclined, and different conditions we will also discuss in the next class. So, with this let me summarize the today's class. We started with very interestingly Bhakra-Nangal for dam projects. If you are all are interested, you just go more data available, but I can say that because of that dam projects, we have changed the irrigations, hydropower generations and water resource management in Himachal Pradesh and part of Uttar Pradesh and all. So, all because of the knowledge of the fluid mechanics way back 1950s and 60s, that was possible. Now, we have more advanced way to understand the fluid mechanics, as I told earlier. So, we can solve many challenging problems apart from the standard problems what we consider it. And that is what we also discuss about the Reynolds transport theorems for linear momentum equations. The problems I have not solved it. In the next class, I will solve the problems and try to know it that how to use the control volume appropriately, so that we can solve the problem with less timing and proper way. That is my point to that. So, you can look at the solve problems or the exercise any of the from any of the reference books. With this, let me conclude this lecture. Thank you.